Hello again. Welcome, part three. Hopefully, the last part. I didn't look to see how much farther we have, but we have two more shapes: Xeo3 and Xe F4. You might think, wait, those are noble gases. They don't form bonds at all. Ha ha ha. You're wrong. Xenon's low in the periodic table, so the electrons are far enough away that they can still get into shenanigans that we'll call bonding. Oh, oh, oh. So I'm putting the valence electrons around these folks. And I sing, connect the dots, la la la. Whoops. Connect the dots, la la. You know my love of one double bond so that I can have resonance structures. So let's go to the right side this time. If you wonder how I decide where it is, I wonder that also. I then have a single electron and a single electron, so I'm going to pick it up and put it over here because double bonds tend not to increase resonance. Remember, resonance makes you more stable. So here I now have 1, 2, the double bond counts as a single area, 3, 4. So I have 4 regions, and 4 regions is tetrahedral. And XeF4, to be honest with you, I've done that one a bunch. It is square planar. And square planar is 2 pairs, 4 bonds. All right. So this next part shows you another way some people get super annoying with their bonds. So I prefer, and I think you know this, oops, oh no, I prefer to connect the dots, then they just leave them as a pair in here. So it's a different format, but be used to it. It's common. So use 3 molecules above to answer the questions that follow. In each case, refer to all 3 molecules when asked to explain or justify. Which of these molecules has only 109.5 bond angles? So 109.5 means 4 regions. Molecule 1 has 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Molecule 1. Here I'd have 1, 2, 3. So this one has 4, 4, 4. This one has 3, 3, 4. This one has, right, so 1, 2, 3. So I'm getting 3, 1, 2, 3, getting 3. And this one has 1, 2, 3, 4. This one has, this carbon has 2. This carbon has 2. This carbon has 3. Oh, 4, not 3. I can count. There we go. 4. 4, 1, 2, 3, 4. Which molecule has the strongest carbon-carbon bond? Strongest carbon-carbon bond is, the answer is going to be molecule 3 because triple bonds are the strongest and only 3 has triple. So this one had a double. This one had a triple. And this one had a home run. Oh, just kidding. They don't do that. So, hitting for the cycle with the carbons just doesn't happen. Which molecule has CCH bond angle of approximately 120? So this bond angle of 120 is 3 regions. Oh, come on, pen. 3 regions equals 120 degrees. And since we labeled them up here before, that means that the double bond, which is molecule 2, only molecule 2 has carbons with 3 regions. Which molecule has the highest percent carbon by mass? Okay, so that one I got to do a little work on. So I'm glad I have my handy dandy calculator. Oh, my screen's not moving. Oh, and we're in the waiting game now. So oh no, if only I could see molecule 1. I think the first one had all singles, and then we had a double, and then we had a triple. So I'm going to go with that. Yeah, that's right. I knew that. So that means I had 3 carbons, so that's going to be 36 plus, what is that, 8 is 44. So the first one has 36 grams of carbon divided by 44 total. The next one, they all have 36 grams of carbon divided by, oops. So 36 grams of carbon for all of them. So then I'll have 36 grams over 44 is molecule 1. 36 grams over 42 is molecule 2. This is my total. So this is carbon, and this is total. This is C plus H total. And this is 36 over 40. So if I really wanted to pretend I didn't have a calculator, molecule 3 would have the highest percentage carbon by mass because it has the greatest amount there. Man, there's more. Use the Lewis dot structures above to answer the questions that follow. Determine the formal charge of every atom in the Lewis structure. Okay, so my super quick cheat ones for Lewis dot structures, and I'll do some other ones, is if singles are bonds, formal charge equals 0. The real formula works though. Formal charge equals valence electrons minus dots, minus bonds, minus dots. Okay, so this one is 0. This one has 1, 2, 3, 4 bonds. That's 0. This one has 1, 2, 3. This one I've got to calculate. So I've got to do nitrogen, and I've got to do oxygen because they don't have the single electron directly in there. So nitrogen equals 5 valence electrons minus 4 bonds equals plus 1. And then oxygen equals 6 valence electrons minus 1 bond minus 6 dots equals -1. And then the other ones are 0. And this guy over here, this one's 0, 1 dot, 1 bond. Oxygen 0 has 2 dots, 2 single electrons, 2 bonds. So these were for the first one. And then carbon, valence electrons 4 minus bonds 3 minus dots 2 equals -1. And then we have nitrogen equals 5 minus 4 minus 0 equals +1. Okay. Determine the formal charge for each one. So +1, -1. Nitrogen over here was +1. Oxygen was -1. All right. Based on formal charge, which of the two molecules the best representation of that? Justify your answer. It is the first one because O is more electronegative and should be the negative formal charge. Nitrogen is more negative and it shouldn't be positive. So that's it. Explain why every bond. Hey, Penny, don't eat. Oh, my dog's taking a towel. Okay. Explain why every bond in CO3 is the same length. We've seen this a handful of times. This is what it looks like. So there are 4 bonds in 3 places in resonance. All are equal. All right. I'm going to show all the resonance structures of this one. It's not that bad. Carbon, 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 carbon. So we have the double bond here, so we're going to move it 1 spot. Skip it. So if we do every other one like that, that's one of them. And yeah, there's the H sticking off. Oh man, there's a lot more of these than I thought. Okay, so then what I could do is carbon, 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 carbon. Okay, and then I can have, so I have 3 double bonds, so I can put them all at the top, right? And then I can do the same thing, carbon, 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 carbon. I'm apparently saying carbon an awful lot, carbon, carbon. So I put 3 double bonds at the top before. So let's put we're just going to rotate our 3 double bonds here. Okay. Same thing, carbon, 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 carbon. Why am I saying carbon so funny? What if I said it happier? Carbon, carbon. So then I put them down there. Now I'll do my double bonds at the bottom. And then, did I do them all at the top already? I did. The first one was the top. So carbon, 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 carbon. And then we'll have the side one. Those would be kind of the bottom left. And then I think all I have left is, yeah, carbon, 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 carbon. Hey, I think I'll say carbon again. And I'll do a double here, double here, double here. And all those H's should be in there. I'm going to try and clean that last one up. It looks not like a carbon. Oh my goodness gracious. Not what I wanted to do. So I'm going to try and make this look a little more carbony. And make this look a little more double bondy. So I just rotated the double bond everywhere. These sticks that I'm putting off here are all hydrogens. But do you see how it gets kind of annoying, how you got to try and put them in different spots? So we did every other one, and then we kind of rotated them all clustered together. I think that's all of them. So let's see. Oh, we got one more question. Determine which structure below is the best based on formal charge. So let's see. Well, let's find the formal charge of each one. So nitrogen, and I wrote my formal charge from a little differently than I usually do. Formal charge is valence electrons minus dots minus bonds. So nitrogen 1 is 5 minus 4 dots minus 2 bonds equals -1. Nitrogen 2 is 5 minus 4 equals +1. Oops. Yeah, minus dots, which is 0 minus 4. And then we have oxygen 6 minus dots, which is 4, minus 2, which is bonds, which is 0. Next one, nitrogen equals, so valence electrons 5 minus 5. So this is going to be 0. I'm shortening this one. 5 minus 4 bonds. 5 minus 4 is +1. And then oxygen is 6 minus 7 equals -1. So again, notice all these are going to add up to be 0. 0 plus 1 minus 1 is 0. On this one, first nitrogen is 5 minus 7, so -2. Next nitrogen is 5 minus 3, which is +2. I already know this one's bad because the numbers are too large. Oxygen is 6 minus 6, which is 0. Over here, nitrogen is 5 minus 7, which is -2. I'm still going to do the nitrogens in order. Nitrogen is going to be 5 minus 4, so it's going to be -1. And then oxygen is going to be 6 minus 3, which is +3. So remember, our goal is to have the lowest formal charges and the negatives on biggest electronegativity. And remember, fluorine has the most electronegativity. So we're going to look for the smallest numbers here. So these guys are out with their 2s and 3s. And on this one, I've got nitrogen with a negative, nitrogen with a positive, and oxygen with a 0. Oxygen should have, O should have the negative. O should be negative. So that's why this is the one we're going to go with. And that's it. Oh my goodness, that took a lot longer for me to explain. But hopefully you only had to check the ones you had to check. And with that, I'll say toodles.